Good morning, students. Today let us start chapter 1.2 Thermodynamic and Kinetic Aspects of Metal Complexes. Okay. Now, what are the thermodynamic and kinetic aspects of metal complexes? Most of the complex compounds are stable. Some of the complexes are stable in one reagent and may dissociate in another reagent. Now, let us consider an example. Dissociation of silver ammonia complex in solution. How it undergo dissociation? Silver ammonium complex, that formula is AgNH3 twice plus gives Ag plus, that means silver ion, and then 2 ammonia molecules. Okay. Next slide. Now, when you write the dissociation constant, K dissociation is equal to the product of the concentration terms of the products of ionization, which are the products from Ag plus and NH3. Okay. So, and then to the power 2. Okay. So, product of the concentration terms of the products divided by the unionized complex, okay, that is AgNH3 twice. Now, this constant is equal to 6 into 10 to the power minus 8, that means it is very low value, okay, minus 8 into power minus 8. So, this shows that the degree of dissociation of the complex ion is extremely small, that is complex is highly stable. If the degree of dissociation is small, means it is highly stable, that means it does not undergo dissociation. Okay. Now, stability complex of the constant of the complex ion is the equilibrium constant of the reverse reaction. So, stability constant is given by the equilibrium constant of the reverse reaction, which is the reverse reaction Ag plus 2 ammonia gives AgNH3 twice plus. Okay. Next slide. The stability constant is given by then AgNH3 twice to the power, okay, plus divided by Ag plus and then NH3, okay, to the power 2. So, stability constant is given by 1.67 into 10 to the power 7. Okay, you can see here the value is very high, that means it is more stable. Now, let us say stability of the complexes. Stability of the complexes, there are two types, okay, that means two types of stability. Now, which are those? Thermodynamic stability and then kinetic stability. Okay. Now, first let us consider thermodynamic stability. This is a measure of the extent to which the complex will form or will be transformed into another species when the system has reached equilibrium. Alright. Next slide. Thermodynamic stability depends upon the strength of the bond between metal and the ligand. Okay. So, whatever strength of the metal bond here in between metal and ligand, that will depend. Cobalt thiocyanate ion, okay, SCN to the 4 times to the power 2 plus. This ion, the bond is very weak and on dilution it breaks immediately and forms another compound. Okay. Now, another type is kinetic stability. Now, what is kinetic stability? The speed or rate with which a transformation leading to the attachment of equilibrium will occur decides the kinetic stability. Okay. Kinetic complexes, there are two types of kinetic complexes, which are those labile and inert complexes. Okay. Next slide. Now, which are called labile complexes? The complexes in which the ligands are readily or rapidly replaced by others, they are called what? Labile complexes. Okay. They should be readily or rapidly replaced. Now, which is the example for that? Copper CuH2O 4 times 2 plus. Okay. This will be pale blue in color, combines with the 4 ammonia molecules, okay, giving deep blue CuNH3 4 times 2 plus 4H2. Alright. Therefore, CuH2 4 times 2 plus is a labile complex. Okay. Now, which are called inert complexes? The complexes in which substitution occurs slowly, they are called what? Inert complexes. Alright. Now, which is a example for that? Hexa aqua chromium 3 plus is kinetically inert complex. Another one is hexa aqua iron 3 plus and hexa aqua chromium 3 plus have roughly the same bond energy. So both have got same bond energy. Okay. But FeH2O 6 times 3 plus is labile, okay, and exchanges its ligands with other ligands rapidly, whereas CrH2O 6 times 3 plus is inert and hence exchanges its ligands very slowly. So hexa aqua chromium exchanges ligand slowly, okay, therefore it is one inert complex, alright, whereas the hexa aqua iron is a labile complex because it exchanges its ligands very rapidly, alright. Now next we shall see stepwise formation constants of the complexes. Okay, so there is a derivation, okay, for stepwise formation of the constant. Now let us consider the formation of the complex MLN. Okay, this is the general formula MLN in aqueous solution. Okay, so MH2O ligand is aqua, water is taken, okay, N times plus L combines with ligand, giving MH2N minus 1 L, okay, aqua. 1 aqua is going outside because here N minus 1, okay, so therefore plus H2. When you write the equilibrium constant MH2, so product to be written in the numerator, so MH2 N minus 1 L, okay, divided by MH2N, okay, and then L. Alright, so there is a overlapping here, okay. So product concentration divided by reactant concentration, alright. Now suppose you have got another reaction, okay, which is another reaction MH2O N minus 1 L plus L, okay. You will get it as MH2O N minus 2 L2 plus H2, okay, same like this, same as first equation. Only thing is your N minus 1 product of the first reaction you are writing here plus L, you will get the another product, okay, you will get here N minus 2, instead of N minus 1 you will get N minus 2, okay, instead of L1, actually it is 1 here, but we do not write 1. So instead of L1 you will get L2, that is all. Other product is water, okay, because one aqua is removed, therefore plus H2, okay. Now equilibrium constant is given by, how do you write equilibrium constant? The molar concentration of the product, which is the product MH2N minus 2 L2, okay, divided by reactant, which is reactant MH2O N minus 1 L into L, okay. Next line. Now suppose you write the product of the second reaction, which is the product of second reaction MH2 N minus 2 L2, alright, plus L. You will get one more less aqua, that means N minus 3, N minus 2 minus one more aqua, that means N minus 3 L3, okay, plus H2, okay. This L will be coming inside this complex, therefore L3 plus aqua, one aqua is removed, alright. For this let us consider equilibrium constant K3. Therefore K3 is equal to product of molar concentration, the product is this one, therefore MH2 N minus 3 L3, okay, divided by reactant molar concentration, which are the reactant, these are the reactants, okay. So MH2O N minus 2 L2 into L, alright, L. Or in general, now how in general how do you write the reaction? MH2O, okay, N minus 1, MH2O N minus 1 plus L gives MLN plus H2. Now for this equilibrium constant, let it be Kn is equal to MLN divided by MH2O L N minus 1 into L. The equilibrium constants are, let us consider K1, K2, K3, in general Kn, they are called stepwise formation constant, okay, these are called formation constants or stepwise stability constants or successive stability constants of the system. They are called by special name stepwise stability constants or stepwise formation constants or successive stability constants, okay. Next slide. Now overall formation constants are cumulative formation constants or stability constant. The formation of the complex MLN may also be expressed by the following. You can write the formation of the complex MLN in another way, which is the other way of writing. MH2O N times plus L gives MH2 N minus 1, that means 1 aqua is less, okay, L plus H2, alright. If we write stability constant as beta 1 is equal to equilibrium constant as stability constant, that is beta 1, okay, MH2O n minus 1, this is the product, into L divided by MH2O n times and then L, okay, ligand. Next slide. MH2O, another reaction, write the product of first reaction MH2ON plus 2L, MH2N minus 2, L2 plus 2H2, okay. So, beta 2 is given by product concentration, you can write MH2O n minus 2 L2, this is the product, divided by MH2O n times, okay, L2, L to the power 2. Similarly, another reaction MH2N times plus 3L, MH2N minus 3, L3 plus 3H2, okay. Beta 3 is given by MH2N minus 3 L3 divided by MH2O n times L cube, alright. Or in general how do you write the same type of reaction, MH2N times plus NL, okay, MLN plus NH2, alright. So, beta n is given by MLN divided by MH2N L to the power n. The equilibrium constant beta 1, beta 2, beta 3, beta n are called overall cumulative formation constants, okay. So, these are called overall or cumulative formation constant. Next slide. Now, what is the relationship between stepwise formation of constant and overall formation of constants? That means relation between K1, K2, K3, Kn, etc. and then beta n. Consider the overall stability constant beta 3 for this third stage. How do you write? Beta 3 is equal to MH2O n minus 3 L3 divided by MH2O n times, okay, L to the power 3. Multiplying both numerator and denominator by MH2ON, okay, L MH2N minus 2 L2. So, when you divide multiplying and by numerator as well as denominator, okay, you will get this form, that is beta 3 is equal to K3 into K2 into K1, okay. Now, this is illustrated by considering these examples. Now, which are the examples for this? Cadmium combines with ammonia to give, okay, cadmium ammonia complex, that is CdNH3 to the power 2 plus. So, K1 is given by 10 to the power 2.65. Now, the product of first reaction combines with ammonia once again, giving CdNH3 2 times, okay, 2 plus. What is K1 value? That is here K1, K2 value is 10 to the power 2.10. Similarly, product of second reaction CdNH3 2 times 2 plus NH3, once again one more ammonia, CdNH3 3 times 2 plus K3 is 10 to the power 1.40. The product of third reaction, that is CdNH3 3 times 2 plus ammonia, giving CdNH3 4 times 2 plus K4 10 to the power 0.93, okay. The value of stability constant decreases, you can see here value of the stability constant goes on decreasing, okay, from K1 to Kn. So, K1 is higher value, K2 less, K3 still less, K4 least, okay. So, we can say that it decreases regularly from K1 to Kn. With K1 is greater than K2, greater than K3, K4 greater than, and finally you will get all will be greater than Kn, okay, increasing the number of ligands. Alright. So, as the number of ligands increases, which are the ligands? Amine ligands. As the number of ligands increases, the K value goes on decreasing, okay. Next slide. Relationship between entropy and stability constant, okay. Now, what is the relationship? The difference between stability and inertness can be expressed thermodynamically. Now, what is the thermodynamic equation? The free energy change is given by standard free energy change delta G naught is equal to minus RT ln beta. So, what is delta G naught? That is standard free energy change is related to equilibrium constant by delta G naught is equal to minus RT ln B, okay, same equation. Suppose you replace this, okay, by what? Ln by logarithm, that means multiply by 2.303. So, minus 2.303 RT log beta, okay. Now, how standard free energy change and enthalpy change, okay, and entropy change are related? They are related by this equation, delta G naught is delta H naught minus T into delta S 1. Let this equation be 2, okay. Now, equate 1 and 2, that means equation 1 is equal to equation 2. What you get? Delta H naught minus T into delta S naught is equal to minus 2.303 RT logarithm beta, alright. From this equation, it follows that complex formation is favored by negative enthalpy changes and positive entropy changes. Okay, enthalpy change must be negative and entropy must be positive. Okay. Now, next is the factors affecting, first factors affecting stability of complex ions. Okay. Now, stability of the complex ions, that means complex compound, depends on many physical and chemical factors. The important contributing factors are due to the nature of the metal and nature of the ligands. Okay. First, let us say nature of the central metal ion, that is charge on the central metal ion. The greater the positive oxidation state of the central metal ion, greater will be attraction for the ligands. Okay. Greater will be the stability of the ligand. So, if the positive oxidation state is greater, then greater will be attraction, then greater will be the stability of the complex. Now, pK values are given for EDTA complexes with the ferrous and ferric ions. Ferrous ion 14.3, ferric ion 25.1. Alright. So, ferric ion carries higher charge. You can see here, this is having plus 2 charge, this is having plus 3. Okay. So, ferric ion carries higher charge and small size. The charge high means it is having small size than Fe2 plus ion, hence Fe3 plus is more stable than Fe2 plus. Okay. Next slide. Then it depends upon the size of the central metal ion. Okay. Stability of the complex increases with the decrease in size of the metal ion. Okay. Another example, pK values of plus 3 lanthanide EDTA complexes, lanthanum 3 plus, 15.50, gadolinium 17.37, cerium 15.98, lutetium 19.83. Stability of EDTA complex of third series of the metal 2 and increases along the series as the size decreases. You can see here, as the size decreases, stability of the complexes goes on increasing. Okay, this is the order of decrease in size. The scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Okay. Next slide. Outer electronic configuration of central metal ion. In the case of metal ions which have same radius and same charge, you can see here sodium ion and copper plus, that is cuprous, calcium 2 plus and cadmium 2 plus. Okay. So, these having same one, the same radius and same charge. Okay. The complex given by metal ion possesses inert gas. Inert gas means 8 electron ions. Pseudo inert gas means 18 electron ions. Pseudo inert gas has 18 plus 2 electron ions are less stable than those given by transition metal ions which have n minus 1 d orbitals available for accepting the electron pairs donated by the ligands. Okay. Next is nature of the ligand. Size and charge of the ligand. High charge and smaller size of the ligand leads to the formation of stable complexes. Stability of the complex given metal ion with halide ion follow the orders. Now, what is the order of halide ion? Fluoride greater than chloride, greater than bromide, greater than iodide. Okay. This holds good for alkali as well as alkaline earth metal ions. But the above order is reversed for palladium, silver, platinum and mercury ions. Okay. Next, it depends upon basic character of ligands. The more basic is the ligands, more easily it can donate electron pairs to the central metal ion and more easily it can form what? Stable complexes. Example, fluoride should form more stable complex than chloride, bromide or iodide. Okay. Then if you compare amine and water as ligands, ammonia is better ligand than water. Okay. Then next is pi bonding capacity of the ligands. The ligands like Cn minus carbonyl ligand and PR3 alkenes, alkynes which are capable of forming pi bonds with the transition metal give more stable complexes. Any ligand which is capable of forming pi bonds, okay, they can form more stable complexes. Then next it depends upon steric hindrance. The bulky group attached to a ligand makes the complex less stable. Okay, if bulky group is attached to ligand, then it makes one less stable. The complex of nickel with the 2-methyl 8-hydroxyquinoline is less stable than 8-hydroxyquinoline. Okay, because here you have methyl group, static hindrance is more here, okay. Here static hindrance is less because of the absence of methyl group, okay. Next, chelate effect. The complexes containing chelate rings are known to be more stable than those containing similar unidependent ligands. This effect is known as chelate effect. Okay. Now, which are the complexes? Cadmium tetra-aqua, you can see here 4 times H2O 2 plus, then methylamine combines to give cadmium CH3NH2 4 times 2 plus 4 H2. Okay. So, this will combine, okay, with the 2 in means ethylene diamine, okay, giving cadmium ethylene diamine 2 times 2 plus 4 H2. So, you can write the same complex in this form, okay, chelatic complex, the cadmium at the center, 1, 2, 3, 4 amine ligands are NH2 attached to CH3 actually, but when you have bond with the other one, you will have CH2 group here, okay, like this. The complex from ethylene diamine is the chelate. You can see the chelatic complex here, and ethylene diamine are known to be 3.1 into 10 to the power 6 and 3.2, okay, 3.2 10 to the power 10, respectively are the constants, alright. Now, I will stop at this stage, okay. So, please go through all the slides. Any difficulty, please contact me, alright. Thank you.